Assalamu alaikum, dear students. Welcome to nuclear physics lecture. And this lectures, we will talk about uranium 235 enrichments. I am Dr. Pervez Ahmad. So let's start our today's lectures with the uranium enrichments. Uh, as you know that all uranium is not created equals. And you should also know that all the elements, some of the elements in the periodic table, they have different isotopes. That is, a sample of any given element usually contains different kind of atoms of that elements. These atoms have different masses. These are called isotopes. So just like that, uraniums also have different isotopes, and these isotopes are the most famous are uranium 238 and uranium 235. Similarly, we can have uranium 234 or uranium 233. So the naturally occurring uraniums are the mostly more widely available uranium is uranium 238. Just like you can see it here in the figure, when we have the ore from the ore, when we do the extractions. So and the extracted ore, we normally have a majority uranium 238. That is, we can say that uh, during the extractions, when we have the uranium and we do the extraction from the ore, so naturally it contains 99% uranium 238, and it contains only 0.711% of uranium 235. And the rest, the smaller amounts, has been the other uranium isotopes that we call uranium 234. So normally you know that for fission reactions or for nuclear weapons or for a generation of electricity during a nuclear reactions, we need sufficient amounts of the uranium 235 that we call the critical mass. So this amount of the uranium 235 that we have, it's the which we can get from naturally occurring uranium, is not sufficient for sustaining a chain reactions. So what actually we do, if this amount is not sufficient, so what actually we do the processing. We need processing to increase the concentration of uranium 235, and that processing is called uranium enrichments. So how we do the enrichment of uraniums, how we can increase the concentrations of the uraniums, this is called uranium concentration. The process in which we increase the concentrations of the uranium 235, that particular process is called enrichment of uranium 235. Before to go into full definitions of the enrichments, let's have a call look at some of the key process that's been involved during the enrichment process. That is, you should know about the rate of diffusions and effusions. So what is the diffusion and effusions? Diffusions basically means a rate at which the two gases mix, and effusion is basically the rate at which a gas escapes through a pinhole into a vacuum. So in other words, we say that the rate is inversely proportional to under root mw. So this is somehow a brief introductions of the diffusion and effusion, because both the diffusion and effusions that are being utilized and uranium's enrichment. Both of these concepts that are being utilized and enrichment of uranium 235. So for effusions of a mixture of two gases, we have a relation that is V1, that is the volume of the first gas divided by the volume of the second gas is equal to under roots masses of the second gas divided by the mass of the first gas. And this particular relation, just like you can see it here, is called the Graham's law. If you utilize these Graham laws for a mixture of hydrogens and helium, so you can get, just putting the values for the hydrogens and helium, that is the volumes of the hydrogens and heliums, and then you put the masses for both the gases, that is for the helium and for the hydrogen gas, and you do the calculation. So out of these calculation you will get values which is equal to 1.414. So what it mean when you do these calculations, I mean you applying the Graham law for the hydrogen and helium gases. So what do you get? You get a values, and what it mean by this value? It means that hydrogen will leave the container faster. I mean, if we do the process, the fusion process, and a container, so it would mean that according to Graham law, hydrogen will leave the container faster. So what it means, if we utilize the same Graham law for the uranium enrichment, I mean we want to get uranium 235 out of uranium 238. Uh, so what actually we get, I mean you just put the values for the masses for the contents. So we get the values which is equal to that equal to 1.009, that is enrichments 1 pass. So here I think is something wrong here with the values, that is the masses. I mean the mass of uranium 35 is 235. It's been mistakenly written as 352. It's not 352. It's basically 253, and here it's not 349. It's basically 238. So you get the values. This value is equal to 1.004. I mean it's the enrichment 1 pass. So and here we utilize UF6 is a source of the gaseous uranium. Sorry. So if UF6 is a source of uranium, gaseous uranium. So here you can see the process here. I mean, gases diffusions, gaseous diffusions uranium enrichment process. So here you can see it here. We have these mixtures, and this mixture, I mean, it's naturally occurring uranium ore. And this week, mostly you can see it here. The blue bubbles, they're basically for uranium 238, while the brown ones, the reddish brown one, you can see it here in between. This is basically for uranium 235. So what actually you do during the gaseous diffusions, you know that we have this porous membrane. I mean it's look like the greenish wall. I mean it's basically the porous membranes. So we pass these gaseous mixtures through this porous membrane and outer passage. You know that on the other sides, here you can see here, before the passage, you know that here's naturally uranium, it contains 0.711% uranium 235, but after being passed through this porous membrane, you can see it here. I mean this is the new concentrations. I mean the enriched uraniums which now increased to more than 1% uranium 235. So this is called enriched uraniums. And what's being left behind, I mean after we getting the enriched uranium from the naturally occurring uraniums. So whatever left behind, we call that depleted uranium. I mean it's the tail that remain behind, we call that depleted uraniums, and it contains an amount smaller than 0.7% of uranium 235. So what we do, if we I mean repeated the process again and again, so we will get further enrichments and uranium 235, and here we will left with the depleted uranium. So enrichment after passing through an fusion barrier is 1.004 whole raised to power, and it is just some sample mathematics for it's for the uranium 235 enrichments. If you do the gaseous diffusions, so the gaseous diffusion stage, it look like here. We utilize high pressures. We have high pressure feed stream. Here you can see it here. It contains uranium 235, and along with that, it has uranium 238 as well. So here you can see it. At the top and the bottom, we have the low pressures. In the middle, we have the barriers. So from these barriers, you see that we have the diffusions either in upward and also downwards. So this is the diffusion. After the diffusions, just like you observed on the previous slide, we have enriched uraniums. So here you see that when the ore passes after the diffusions, what left being here, it passed through this just like this beam, this stream. It's a depleted stream. It's the uranium that been remain after we remove the enriched uranium. So what's being left behind, we call that depleted uranium. So it goes this way. In the upper stream, we have the enriched uranium. So enriched uranium in the upper stream, and in the middle of the stream that we left is called the depleted stream. So what actually we need 2.1% of uranium 235 to run light water reactors. I mean, it's this is the basic requirement for running the low water reactor. That is 3 times the natural concentrations of the U235 has been required. It's naturally, you know that naturally occurring uranium contains 0.711% of the uranium 235. So what actually you need to do, we require 2.1% uranium 235. So what actually you do is mean that we have 3 times natural uranium concentration. So what actually you do, as we have the relation that is 1.004 whole raised to power n. So here instead of n, we have to put the values, that is 263. So what actually we get values equal to 3. So what it mean? It mean that 263 diffusion stages are being needed to get this amount of the uranium for light water reactor. So what it mean? It means that large amount of the energies is being required to push uranium through so many barriers. If you want to have this much of the enriched uranium, so what actually you do, this is a sample formula just like we have it on the previous slide. Here we have this formula that is 1.004 raised to power n. So n basically the the number we have here, that is the time. It's n is basically here for the number of time, that is the here we say that 3 times natural concentrations. So we just put the values here and we do the calculations. So the diffusion stages here 263 diffusion stages. It's mean that large amount of energy needed to push uranium through so many barrier, which is I think is very difficult task to do. So that's all we have for uranium 235 enrichment and this particular lectures. The further detail you can go to different website. You can get data from the different nodes. You can watch some of the videos, other videos available on the YouTube, and at the same time you can have a look on the books. There's plenty of book available on the Google's book, and you can also get a book from some of your school or college or university library. So that's all we have for this lecture. I'll see you for more lectures. Till then, bye bye.